let's just jump right into this explainer. We're going to explore the hidden architecture that actually makes our software run efficiently. Because, whenever we interact with our computers, our phones, or honestly, even our smart appliances, there is this massive amount of invisible organization happening right beneath the surface. Today, we're going to demystify exactly how all that works. We've all been there, right? You click a button and the screen just freezes. It's so easy to just blame an old phone or maybe a slow internet connection. But the secret sauce to speed isn't just about having better hardware. The real magic, or, well, the real bottleneck, usually comes down to how the foundational data is actually organized. So, what does this all actually mean? The absolute crucial point here is understanding exactly what a data structure is. Put simply, it's just a specific way of organizing data so it can be used effectively. A good data structure saves you both execution time and memory space when you're processing, retrieving, or storing data. It's like a giant puzzle. The way you structure your data and the algorithms you write are completely tied to each other. Get the structure right, and your operations become lightning fast. Here's how we're going to map out the 11 most popular data structures used in programming today. We'll start with the fork in the road, look at the linear lineup, then we'll branch out visually, look at some specialized organizers, and finally we'll cover real-world applications. Okay, section 1, the fork in the road, linear versus nonlinear. Let's see how this builds the foundation for everything we're about to discuss. This brilliantly illustrates that basic split. Every single structure essentially falls into one of these two camps. On one side, we've got linear data structures. This is where elements are arranged sequentially, just in one single dimension. On the flip side, we have nonlinear data structures. Here, elements are arranged in way more complex dimensions. Think one-to-many, many-to-one, or even many-to-many relationships. So your data is either traveling in a straight, totally predictable line, or it's branching out in multiple, complex directions. Moving right along to section 2, the linear lineup, straight lines. Let's look at structures where data follows a clear one-dimensional sequence. First up in this lineup, we have arrays and linked lists. These are basically the two fundamental ways to store a sequence of items. An array is a collection of items of the exact same type, and they're stored at perfectly contiguous memory locations. Because they sit right side by side like that, it is incredibly easy to calculate the position of any element. You literally just add an offset to the base memory location. But a linked list? It takes a totally different approach. Unlike arrays, linked list elements are not stored contiguously. Instead, these scattered pieces of data are brilliantly linked together using pointers. This means if you suddenly run out of contiguous space, no problem. A linked list can still flexibly string your data together. Next up is the stack. You can think of a stack exactly like a stack of plates in a cafeteria. It strictly follows a last-in, first-out order, or LIFO. You are only permitted to insert and delete items from one specific end of the list. So you use a push operation to insert an element right onto the top, a pop operation to remove the most recently added element from the top, and a top operation to just peek at that last element without actually removing it. Now a queue, on the other hand, operates completely differently. It is first in, first out, or FIFO. This is exactly like waiting in line at a coffee shop. The first customer who arrives is for sure the first one served. You use an NQ operation to add an element to the rear of the line, and a DQ operation to remove an element from the front. And if you just want to see who is next in line without actually removing them, you simply use a peek, sometimes called a front operation. Okay, on to section 3, branching out visually, nonlinear networks. This is where relationships get hierarchical and a lot more complex. The most iconic nonlinear structure is absolutely the tree, specifically the binary tree. So unlike those linear lists we just talked about, a binary tree organizes data hierarchically. It starts with a pointer to the topmost node, which we call the root, and the golden rule of a standard binary tree is that each node can have at most 2 children. We simply refer to them as the left child and the right child. Now this is where it gets really fascinating. What's super interesting here is how adding just one simple sorting rule completely transforms a standard binary tree into a highly searchable structure called a binary search tree. By ensuring that all keys less than the root are stored on the left and all keys greater than the root are stored on the right, you create a system that can be searched incredibly fast. Plus, a true binary search tree ensures there are absolutely no duplicate keys present. It's so efficient.
Building on that concept, we have heaps. Heaps are these special complete binary trees that are completely obsessed with hierarchy. They constantly maintain either the absolute maximum or the absolute minimum value right at that topmost root. So in a max heap, the root node key must always be the greatest among all its children, and that property recursively holds true all the way down the entire tree. A min heap, as you probably guess, is the exact opposite. It ensures the absolute minimum value sits right at the top. Moving beyond those hierarchical trees, we run into graphs. A graph is basically a collection of nodes, which are also called vertices, and they're connected by edges. For mapping complex webs of relationships, this is hands down the ultimate tool. Whether we're talking about modeling a massive social network where the nodes are people and the edges are friendships, or even a transportation network mapping out complex city streets, graphs allow us to model incredibly complex, real-world systems. Which brings us to Section 4. Specialized organizers, the experts. Let's look at 3 highly specialized tools built for specific, rapid-fire jobs. First up are hash tables, and these are the absolute speed demons of data retrieval. They mathematically convert values into direct memory addresses for literal instant access using something called a hash function. For example, a hash function might map a value by calculating x modulo 10, which, if you remember your math, is essentially just finding the remainder when something is divided by 10. So if you have a list of values like 11, 12, and 13, the hash function instantly tells the computer to store them at positions 1, 2, and 3 in the table. The efficiency of your data mapping honestly depends entirely on how clever your hash function is. Next, we have the matrix. A matrix gives us a really rigid mathematical grid of rows and columns, beautifully enclosed in brackets. This structure is totally essential for mathematical computations, transformations, and really anywhere you need to represent data in a strict two-dimensional grid format. In fact, if you've ever wondered how 3D graphics are rendered so smoothly on your screen, well, you have matrices to thank for doing all that heavy mathematical lifting. And then we have the trie, which is sometimes called a prefix tree. The trie is the absolute ultimate text search specialist. If you were to try and store string keys in a standard balanced binary search tree, your search time would be proportional to the maximum string length multiplied by the logarithm of the number of keys. It gets heavy. But using a trie, it brings that search complexity all the way down to the optimal limit of just the key's length. Meaning you can search in what we call O if M time, where M is simply the number of letters in the word you're looking for. It is blisteringly fast. The only catch, because there's always a catch, right, is that it trades away storage space to achieve that incredible speed. Finally, Section 5, real-world applications where it all lives. Let's see how these theoretical concepts actually run our modern world. Because these structures, they are literally everywhere. Operating systems rely heavily on queues and heaps just to manage basic tasks. Graphics and image processing use matrices all day long. Computer design, complex simulations, and even mapping human genetics rely on really complex graphs and trees to make sense of billions of data points. And the security of the blockchain itself, it's fundamentally built on cryptographic hashing and linked structures. These 11 structures we've covered today are genuinely the invisible scaffolding of virtually every digital breakthrough we enjoy right now. Which brings us to a final thought. If data is the new oil of the modern economy, then data structures are the complex pipelines and refineries that make it actually useful. Seeing how mathematically precise and efficient systems can be at managing massive, complex networks, it really leaves us to wonder, with all this incredible architecture available, how efficiently is our own daily data truly being managed? Thanks for exploring this with me today. I hope this gives you a whole new appreciation for the hidden architecture right behind your screen.